To summarize what we did, to recap, we have now looked at what happens when we take white Gaussian noise and we send it through a filter. So where did we start? I mean, we started here with this picture, that we have white Gaussian noise and it goes through a filter with some impulse response H, and then we get an output W. And then we have looked at what is the distribution of W, and we argue for that it's a Gaussian random process, which means for every value of t, we have a Gaussian random variable. And then the mean, the average of that Gaussian random variable is 0. Okay? And then the last calculation we did was to figure out the variance of the Gaussian random variable, and we got that to be n0 over 2 times EH. So if we want to summarize what we have learned now, is that we have learned that W of t, the output of a filter, which with the impulse response H, when the input is white Gaussian noise, if we take that random process and we take a sample of that, we look at the amplitude of that Gaussian process at any time t1, just any time whatsoever. This is a Gaussian random variable. So, so it's a Gaussian random variable with 0 mean and variance n0 over 2 times EH. Okay. So this is a very important conclusion. Okay, so I'll put that inside red. Okay. So we now know that if we take white noise and we filter it, we get something which is much more well behaved. So instead of having something where we take samples where we have infinite variance, if we now take samples, we get something which has finite variance, and the variance is given as n0 over 2 times the energy of the filter impulse response. Okay. So whatever filter we choose, the energy of its impulse response is important. That's the only thing which is important for the noise from a noise point of view. Okay. So the shape doesn't really matter, only the energy. Okay. So going back to where we are looking at this type of scheme, right? So we have some amplitudes that carries data that we would like to decode at the detector. What we have looked at now is the let's see, so you can actually see this. So what we have seen now is that the noise, which is the bad guy in this scheme, how if we model that as white Gaussian noise with power spectral density n0 over 2, as we have done, we see that when the noise is going through the filter, we get this W of t here. Okay. The difference from the derivation we just did and from this setup here is that we have an impulse response now which is matched to the pulse that we are transmitting. So it's matched to H. But we remember that the statistical properties of W only depends on the energy of this impulse response, not its actual shape. So the energy of the matched filter impulse response, so what is the matched filter impulse response? Well, it's a conjugation that does not change the energy, and it's a time reversed version of it. It does not change the energy of H, which means that the energy of this impulse response is exactly the energy of H. Okay, so the derivation we just did holds for this setting also. Okay, and then the next step, what happens is that we sample W, and we sample that once every t seconds, and then we get a number Wk here, where let's see, Wk. What do we know about Wk? Well, we knew from before that it's a Gaussian random variable with 0 mean, and it has a variance which is n0 over 2 times EH, like this. So now we know the statistical properties of W. Okay. Then, to calculate now the error probability, we would like to characterize not W itself, but rather this variable, zk here. That's the input to the slicer device. So what is the input to the slicer device? So z of k is equal to a of k, assuming that h is a root raised cosine pulse, root Nyquist pulse, which we assume. So there is no intersymbol interference. And then it's plus the noise contribution. And what is the noise contribution? Well, it's W of k and then divided by EH. Okay. And the division by EH comes from going from here to here, where we divide by EH. Okay. So ZK is equal to AK plus WK divided by EH. Okay. And we write the noise contribution here as simply NK. Okay, where NK is equal to WK divided by EH. Okay, and it's a Gaussian random variable. What mean does it have? 0, exactly. And variance? N0 2 times EH. No. Sorry, that's not true. Yes, it's true, of course. Okay. So where did, sorry, let's write this out. Just 1 second. Here we go. From the beginning we had it like this, n naught over 2 divide. Now, okay. We started by having n naught over 2 divided by EH like this, and then we need to multiply with EH squared, right? Because this is what we did. Let me begin again. Okay, so what did we start with? We started with that WK has variance n naught over 2 times EH. So let's start with that. Okay, and then when we divide through by EH, we change the variance by dividing the variance with EH squared. Okay, and therefore we get that the variance here is n naught over 2 EH. Okay. And since this is a little bit cumbersome to write, we'll call that sigma squared. All right, so what have we done now? Well, now we know the statistical properties of ZK here, or what ZK is. It's AK, the transmitted symbol, plus a noise contribution NK, and NK is a Gaussian random variable with 0 mean and variance sigma squared, where sigma squared is equal to this. So what we would like to do now is to be able to calculate what is the error probability. And the error probability is the probability that the output of the slicer is not equal to the input of the pulse amplitude modulator. Okay, so that's the probability of a symbol error. So when A hat k is not equal to AK, that is a symbol error, and we would like to calculate the probability for this to happen. Okay. So let's do this for an example when we use pulse amplitude modulation, and just see how we can actually calculate the error probability here. Okay. So let's start first by drawing up the constellation. Okay. So along this axis is the input to the slicer. And so let's look at one particular symbol here. It really doesn't matter which symbol to choose. We have zk equals ak plus nk. So it's the same for all k's. So let's just drop the k variable here. So k means the kth symbol. So let's just look at z as equal to a plus n. Okay. So the input to the slicer device then is z, some input. Okay. It doesn't matter which of if the first, second, or third, or fourth, or something. We just take one out of this sequence of symbols because all of them will behave in the same way. And what we need to do then is to figure out the decision regions for our constellation. So suppose we have now 8 PAM. Okay. If we have 8 constellation points here, let's draw them in here. So we have one here, say, one here, one here. Now we're up to 4, 5, 6, 7, and 8 points. So here we have our constellation points. And then we have decision boundaries between these points, which goes through the midpoint, like this. And then we need to enumerate these. So we call the first point here A1 and the last point A8. And somewhere in between we have 0, and which means that to the far left we have -7. Okay. What we do also, we have equidistance. So the first point is at C, the other point is at 2C, the 5C and 7C to the right here. So the distance between 2 points is 2C, like this. So we have -5C, -3C, and -C here. Okay. And C is some constant that we have chosen. Okay. So here we have the constellation. And what we would like to do now is to say what is the probability that we end up in the wrong decision region. So for simplicity, suppose that we transmit this constellation point, A1. Okay? Suppose that this is what we transmitted. When do we make an error? Well, we make an error when the input Z is to the right of the decision boundary, because then we end up in this decision, this decision, this decision, or whatever, right? But if we end up to the left of this decision boundary, then the decision from going, oh, maybe I should change color here. Here. When we end up to the left of here, then our decision A hat is equal to A1, right? Because then all the points on the z-axis, which is to the left of the decision boundary here, is closer to this point than to any other point, so the output is A hat equal 1. If we go to the right here, then A hat will not be equal to A1, right? Which means that we make an error as soon as we're to the right of the decision boundary. So the probability of error, symbol error, if we transmit the first symbol, so it's denoted like this, P and subscript E, vertical bar, means conditioned on that we have transmitted symbol number 1. Okay, so this is the probability of error given that A, the transmitted symbol, is equal to A1. Is the probability that Z is not let's do it like this instead. That Z is greater than what value? Well, it's greater than the value of the decision boundary, which happens to be at negative 6C. Oops. Conditioned on that what we transmitted was the first symbol, namely that A is equal to negative 7C. Okay, so what is Z? Z in general is A plus N. So, which means that if A is equal to negative 7C, Z is equal to negative 7C plus N. Right? So if we continue here, we see that PE1 is then the probability that minus 7C plus N is greater than minus 6C. Why is that? Well, it's because conditioned on that A is negative 7C, then Z is negative 7C plus N. So that's what we have here. And the right-hand side of the inequality is the same, minus 6C. Okay, and then we can write this as the probability that N is greater than C. Okay. So, what is this probability? Well, what do we know about N? Let's go back and check. So, we know that the noise is a Gaussian random variable with zero mean and variance sigma squared. Okay, so therefore, this probability is very simple to calculate. We simply take the noise and we divide through by the standard deviation, and then we can use a Q function. Okay, so because here we have something which is distributed zero mean Gaussian with variance 1. So this is equal to the Q of C divided by sigma squared, sigma like that. Okay, and for reasons that will be more obvious later on, we will write this as the Q, or the square root of c squared divided by sigma squared, which is the q of c squared, and then we'll put in what sigma squared is, which is n naught over 2 divided by EH. So here we have n naught and then 2EH here. And what we will see momentarily is that we can relate sigma c squared here to the average energy per symbol. We'll see that shortly. Okay. So what have we done now? So let's recap. We have said, okay, suppose we transmit this point, this blue point. What is the probability of error? Well, the probability of error occurs if we're to the right of the decision boundary, which we then went through a few things, and we see that this is the probability that noise is greater than C. Okay? And maybe we could have figured this one out already from the beginning, because if we transmit this point, the receive point Z would be this point plus the noise. Okay? Which means that if the noise is negative, then there is no problem. We move from this point to the left. If the noise is positive, we move to the right. And it's a problem when the noise exceeds the distance from the transmitted point and the decision boundary, which happens to be C. Okay? So we make an error if the noise is greater than the distance to the decision boundary, which is in this case C. Okay? So we could have drawn up this equation immediately, right? If we wanted to. But now we took the long route. Okay, so now we know the error probability if we transmit this point. But what is the error probability that we transmit this point, for instance? On this side. What do you think? Same. Why?
It's symmetric.
This is what you say on the exam, right? Due to symmetry, it's clearly seen that this is the case, which is true in this case, right? And if it's true on the exam, you will get nice points for that too, right? But it's completely symmetric. You know, it's a zero mean Gaussian random variable, so it's this symmetrical bell shape. So whether we look at the left-hand tail or the right-hand tail, it's the same. Okay, so this is equal to the probability of error if we transmit also the 8th signal alternative. Okay, and then we just have the inner points here to worry about. And we see that due to symmetry, all the inner points are equal also. So we can just pick one of them and figure out what is the error probability for that. And then we have characterized all the possible error probabilities that could occur in this case. And to do that, we zoom in on one of these and draw it a little bit more zoomed in version of this one. So we take one of these midpoints and we put it in the middle, and then we draw out the decision boundaries like this. Okay, so this is one of the midpoints. So the distance to the decision boundary here is still equal to C in both directions. Okay. So the probability for error here, what is that? Well, it's the probability. So this is, okay, so let's draw this. So this is what we transmit, A. Okay, so this is the transmitted, right? And Z that we get is A plus noise. So as long as this point is inside the decision boundary, we make no error. But we make an error when the noise pushes this over this decision boundary or over this decision boundary, right? So we have two decision boundaries to worry about here. So the probability of error occurs if n, the magnitude of n, is greater than C. right? Because then we fall off the left-hand side or the right-hand side. And we can write this as the probability that n is greater than c plus the probability that n is less than negative c. And we continue up here and see that these are symmetric. So it's 2 times the probability that n is greater than c. Okay. And why is that, by the way? Well, if we look at the Gaussian PDF here, we have some, I don't know, some Gaussian like this. And if we look at, oh, this is a horrible drawing. I see. I really need to make this symmetric now. You can sort. It's not going to be any better than this. So if we have c here, this is the probability that n is greater than c, and the same tail we find to the left here. If we have negative c here, so this is the probability that n is less than negative c. Like this. Okay. So it doesn't matter, both ends are the same. So that's why we can do this. Okay, and this we learned already earlier that this is PE1. Okay. So now we know the probability of making an error for an inner point and the outer points. So what is the average probability of error? Well, we average over all these points. And although these points are transmitted with equal probability 1 over m, so the end result is that the probability of error is 1 over m sum m n equals 1 to, sorry, sum L equals 1 to m of the probability of error, condition on that we transmit the LF symbol. So this is 1 over m, and we have 2 times PE1. Okay, so these are the outer points. Plus, how many inner points do we have in general? Well, we have m minus 2 inner points, and it should be multiplied with the same number, PE1, times 2. Okay. So outer points and inner points. Okay. And I will spare you the algebra here, because what we do is we take these Q functions, we add them together and so forth. And at the end of the day, we get 2 times m minus 1 divided by m of these Q functions. And what is the argument of the Q function? Well, we said earlier that the argument of the Q function is c squared divided by sigma squared. Okay. Now, in the lecture we had last... no, we still have 15 minutes, right? In the last lecture, we did a calculation that related c squared and the energy per symbol, if you remember this. And I will just quote the result here. We know that for Emery PAM, with distance 2c between points, and equally likely transmitted symbols C squared is equal to 3 times the energy for the alphabet, EA, divided by m squared minus 1. Okay. Okay. So, and we recall from before that sigma square. What was sigma square? Okay, so let's go back and see what sigma square was. Okay, where do we have it? Where do we have it? It is, here we go. So sigma square is n naught over 2 EH. So it's, oops, I don't want to do that. I want to do this. That is n naught over 2 EH, like this. Okay, so c squared over sigma squared is simply 3EA divided by m squared minus 1 times 2EH divided by n naught. Okay, and this is equal to 6 times EA times EH divided through by m squared minus 1 times n naught. And now we see that in the numerator we have EA times EH. Do you remember what that is?
ES.
ES, exactly. So here we have 6 divided by m squared minus 1 times ES over n naught. Okay. This ES over n naught has a tendency of popping up all the time when we do these type of error calculations. So this is sometimes known as the SNR per symbol. Okay. And it's SNR per symbol because we have ES over n naught. If it was EB over n naught, EB over n naught, that would be the SNR per bit. But to finalize everything, the error probability we have is then 2m minus 1 divided by m q square root of 6 m squared minus 1 times ES over n naught. Right. So, my friends, what we have done now is we've been able to calculate the symbol error probability for M-ary PAM over a white Gaussian noise channel. That's not bad for a Friday afternoon, actually. So, what can we learn from this equation except that there has Q function? So the dependency, what does the error probability depend on? Well, it depends on M, and then it depends on ES over N naught. Okay, so these are the important things. And ES over N naught depends on the strength of the noise of the channel. So this is what's given to us. And ES is the energy that we spend per transmitted symbol. So we can change that by changing the transmit power. The more power, the higher ES is. Or for a fixed power, we can change ES by changing the time between samples. Okay, so if we have a fixed power and we let a symbol take long time, it gets high energy. Okay, so we can play around a little bit with ES. That's under our control. And M here is a design parameter of ours, right? We can select that. So M and ES are designs, and naught is the physical nature of the channel which is given to us. Okay. But if we go back and look then at these type of plots, to see, okay, what is the symbol error probability as we vary things. So, the pulse amplitude modulation symbol error probability. Okay, so what we have here plotted on the vertical axis here is the error probability in log scale. Okay, so you see it's log scale here. On this axis here, we have plotted the signal to noise ratio per symbol also in log scale, or dB scale if you like. So this is also known as ES over N naught in dB. Okay, so this is typically how these plots are. They're basically log plots of error probability as a function over ES over N naught. And for a fixed N naught, when we go to the right here, that means that we increase the transmit power. So that's a usual way to think of this. So this, by increasing the power, we go along this axis. So if we then select M equals to 2, we see that the error probability for low power is pretty high, and then it falls off very sharply down to 10 to the minus 3 at, I don't know what that could be, 6 dB maybe of signal to noise ratio. So we see that the error probability falls off very quickly as we increase the signal to noise ratio. Now, if we go from M equals 2 to M equals 4, we also have this decay, but we need more power to reach this error probability of 10 to the minus 3 compared to M equals 2. As a matter of fact, every time we double the signal alphabet size, which means that we add 1 bit to the signal constellation. So this is 1 bit, 2 bits, 3 bits, 4 bits, 5 bits, and 6 bits, right? So every time we increase the signal constellation with 1 bit, we have to pay approximately 6 decibels in power to get the same error probability. Okay, and 6 dB is 3 plus 3, which means that we need to quadruple the transmit power. Okay, 6 dB is a 4-time increase. So by getting 1 more bit per symbol, we have to crank up the power with a factor 4. Okay, so this scales pretty badly in power, right? Because we cannot increase power indefinitely because of safety reasons, and also because maybe if you have a battery powered device, you don't want to, right? Because then you would drain the power quickly. Okay, so increasing M, why do we want to do that? Well, it has some good things with it. It increases the spectral efficiency, because we know that the spectral efficiency is 2 times the log 2 of M divided 1 plus alpha. And alpha is whatever excess bandwidth we use. It's not necessarily the alpha of the root raised cosine positive that we use. But the problem is that by increasing the spectral efficiency, we decrease the power efficiency because we need 4 times as much power in order to support the same error probability. Okay. So we have spectral efficiency, we have power efficiency. You want to increase the spectral efficiency, you reduce the power efficiency. You want to increase the power efficiency, you decrease the spectral efficiency. Gungor och karuseller. Right? We can trade one for the other, but we cannot increase both at the same time. Life. Okay. How about bit errors? And here, because that's what you do in the project, right? So you're not concerned overly about symbol errors. There's a requirement on the bit error probability. When you make a symbol error, you will make bit errors, for sure. But how many will you do? Well, if we consider a modulation format where we have m symbol alternatives, that is 2 to the power of k, where k is the number of bits, then each symbol error, okay, so if we have a symbol error, what can we say? Well, we can say that we have at least 1 bit error, right? Because we know a symbol carries a number of bits, k, and as soon as one symbol is wrong, then this bit pattern is wrong. So at least 1 bit must be wrong. The other bits could be correct, but at least 1 bit has been flipped. Okay. So a symbol error gives at least 1 bit error, but then at most k bit errors. In practice, it's some number in between, and we don't know what. Okay, so let's calculate the extreme cases. So one extreme case is when all bits are wrong. So whenever we do a symbol error, all bits for some reason are wrong. Then the bit error probability is equal to the symbol error probability. However, in the other extreme case, when only 1 bit error is wrong, only 1 bit is wrong when we make a symbol error, then the bit error probability is 1 over k times the symbol error probability. Okay, and why is this? Well, remember that we have k bits here, b0, b1, up to k minus 1. These are the bits that we transmit when we transmit the symbol. When we make a symbol error, one of these bits are wrong, but the rest are correct. Right? So k minus 1 bits are correct, and one is in error. So the okay, we're running out of time. So trust me on this one. If you have problems with this, we can talk about it next time. So anyways, for all systems, we have something where the bit error probability is in between these two extremes. It's less than the symbol error probability, but it's greater than 1 over k times the symbol error probability. One final thing. Here's the formal proof. Gray codes. Okay. Can I get 2 minutes of your weekend? 3? Okay. For PAM and QAM, the most common symbol error is to the closest neighbor, right? So if we have our signal points here, the error I do is most likely to the neighboring one, because that has to do with the noise. The noise goes, it's more improbable that it goes far than slow. So this error probability error event is more likely than this error event. So what we would like to do is to minimize the number of bit errors we do when we move from one point to the other point. Okay, so if we make the bit patterns for neighboring symbols differ in only one position, they have to differ, right? But the least amount of bits they have to differ in is one position. Then we tend to make only 1 bit error 1 bit error per symbol error, and such mappings are called gray codes. So if we want to look at one way of enumerating these points, so think of these as the constellation points on a PAM scheme, and here is the corresponding bit label. So going from here to here, there is only one bit that changes. Here is only one bit that changes. Here is only one bit that changes. It looks good, but here 3 bits change. See, all bits are flipped here. So if I transmit this pulse and make an error like this, then all my bits are lost. Okay, and so forth. But in gray code, we see that when going from one to another, only one bit changes. And this is a property of the gray code. And you can check for yourself that this is true. So gray codes here are typically used when we want to minimize the bit error probability for a given symbol error probability. The symbol error probability we can fix by changing m and the transmit power, but then given to minimize the bit error probability for the symbol errors that we have, we can use gray mappings. So that's a pretty clear indication that in the project you should use. Okay, I'll let you think about that during the weekend. Okay. So see you on Monday.